Hello. So in today's discussion, we are now in section 10, and we will be working on some series where we determine whether those series are absolutely convergent, conditionally convergent, or divergent. So before we begin on those examples, let us recall the definition of absolutely convergent series or conditionally convergent series and the theorems that will help us determine whether a given series is absolutely convergent, conditionally convergent, or divergent. So we recall the definition. So a series, sum an, this is absolutely convergent if the absolute series of the absolute values, sum absolute value an, is convergent. So you start with this series, okay? And then you take the absolute values of the terms, and then you now have a new series. So you determine whether that new series is convergent or divergent. If it is convergent, then the original series is absolutely convergent. Now, if the series an is convergent, but the series absolute value of an is divergent, then we say that the series an is conditionally convergent. Okay? So there are possibilities where the original series is convergent, but if you put now absolute values on the terms, the series or the new series will be divergent. So those series are said to be conditionally convergent. Okay? So the first theorem that we will use is called the absolute convergence test. And this states that if the sum an is absolutely convergent, meaning the sum absolute values of an is convergent, then this series, sum an, is convergent. Okay? So we can look at it this way. So the sum of the absolute values of an is convergent. This implies that the sum of an is also convergent. Okay? So every series that is absolutely convergent is also convergent. Okay? Next theorem, we have the ratio test. Okay? So suppose now we have a series an with non-zero terms. If the limit of the absolute values of the ratio a sub n plus 1 over a sub n is a real number that's less than 1, okay, then this series here is absolutely convergent. Okay? And therefore, this series here is convergent. Okay? However, if the limit of the absolute value of the ratio a sub n plus 1 over an is a real number greater than 1 or is plus infinity, then this series here is divergent. Okay? So you are comparing the limit of the ratio a sub n plus 1 over a sub n in absolute values with the number 1. So either less than 1 or greater than 1. Now, if the limit is equal to 1, okay, then the test is inconclusive, meaning we cannot conclude anything about this series. So in order to determine whether the series is convergent or divergent, we have to use another test. Okay? The last theorem that we need to recall, it's called the root test. Okay? So here we are given a series, a sub n. Okay? Now, if the limit of the absolute value of an raised to 1 over n, okay? So limit of the absolute value of an raised to 1 over n is a real number that is less than 1, okay? Then the series an is absolutely convergent and is therefore convergent. If the limit of absolute value of an raised to 1 over n is a real number that is greater than 1 or is plus infinity, then the series an is divergent. So notice, this is very similar to the ratio test. And again, you compare the limits with 1. So either less than 1, in that case, you have absolutely convergent series. And then you have greater than 1. In that case, the series is divergent. If it is equal to 1, then this root test also fails, meaning the test is inconclusive, just like the ratio test. So, in order to determine whether this series is convergent or divergent, you have to use another test. Okay? But do not try ratio test. Okay? Because if you try ratio test, you will also get a limit equal to 1. So don't try the ratio test. Okay? So now let us proceed with our examples. Our goal is to determine whether the given series is convergent or divergent. And if it is convergent, we will determine whether the convergence is absolutely or conditionally. So let's start. So we have the series -1 raised to n minus 1 all over n cubed plus n minus 1. Okay? So in here, let us look at the denominator first. So notice that your n starts from 1 and it just increases. Okay? N equals 1, 2, 3, etc. And you have to observe that your n cubed plus n minus 1, okay, this is always greater than 0. Okay? And why is that? Look, for, so this is the reason. For n equals 1, 2, 3, etc. Okay? Your n minus 1 is greater than or equal to 0. When n equals 1, you have 0. When n equals 2, you have 2 minus 1, which is positive now. And of course, as you increase your n minus 1 will be positive. So this means that your n cubed plus n minus 1, this is greater than 0 for all n. For all n equals 1, 2, 3, etc. So what does this mean? This is positive, okay? Which means that 1 over this guy here, it's positive, okay? And then you have the term -1 raised to n minus 1. Therefore, this guy here is an alternating series, okay? So let us write those details. So here you have your 1 over n cubed plus n minus 1, okay? This is greater than 0 for n, for all n equals 1, 2, 3, etc. Okay? Which means that the series -1 raised to n minus 1 over n cubed plus n minus 1, and from 1 up to plus infinity. Okay? This one is alternating series. Alternating series. So you can actually check, or you can actually use the alternating series test in order to determine whether this guy here is convergent or divergent. Okay? But in order to determine whether this guy here is absolutely convergent or conditionally convergent, we have to consider the absolute values. Okay? So we now consider, the series with the absolute values. Okay, so -1 raised to n minus 1 over n cubed plus n minus 1, and from 1 up to plus infinity. We consider this, okay? But this guy here, you can just write this as 1 over n cubed plus n minus 1, and from 1 up to infinity. You get the absolute value of -1, it's just positive 1. So if you consider this, okay, remember the hint that I mentioned before. So in here, you can compare this series, okay, with the series whose term is 1 over n cubed, correct? 1 over n cubed, okay? So compare the series, compare, let me label this as a star, compare star with the p series 1 over n cubed, and from 1 up to plus infinity, okay? A p series, okay, this is a p series with p equals 3 greater than 1, which means that this guy here is convergent, okay? So sum 1 over n cubed, and from 1 up to infinity, this is convergent, okay? Now observe that your n cubed, this is less than n cubed plus n minus 1, okay? Or less than or equal, okay? All n, for all n greater than or equal to 1, which means your 1 over n cubed, okay? Your 1 over n cubed plus n minus 1 will be less than or equal to 1 over n cubed, correct? Take note, this guy here, well, this guy here, it's always positive. So, so let me put that part. So this guy here, it's always greater than or 0. So we will not have any problem with this inequality here. So this series is convergent, meaning the one bigger is convergent, okay? This guy here, which is smaller, will also be convergent, okay? Therefore, the series 1 over n cubed plus n minus 1 as n runs from 1 to plus infinity. This is convergent, okay? Convergent by comparison test. So we just use comparison test, okay? Therefore, the original series here is absolutely convergent because this guy here is convergent and this is that one, okay? So to conclude, let me just write it there. So sum -1 raised to n minus 1 over n cubed plus n minus 1, and from 1 up to infinity, this one is absolutely convergent, okay? Question, okay? So again, originally this guy here is an alternating series. So you can actually use your alternating series test. But take note that the alternating series test only concludes convergence or divergence. Okay? If the series is convergent, it does not tell you directly whether the series is absolutely convergent or conditionally convergent. So you really have to pass through this process. Okay? You get the absolute values of the terms and move and calculate or determine whether it is convergent or divergent. Okay? So question. Let's consider now this the next series here. So sum -1 to the n sine of 1 over n running from 1 up to plus infinity. Okay? So let's check. First, it looks like it's an alternating series. Okay? But actually, we will see that this is indeed an alternating series. So the only thing that we need to show is that this sign of 1 over n is always positive. Correct? The sign of 1 over n is always positive. Okay? But note, note, note here that note that if say z, okay, if z is between, okay, is between 0 and pi over 2, okay, 0 and pi over 2, okay, then sine z, it's greater than or equal to 0, correct? It's 0 at z equals 0 and positive between 0 and pi over 2, okay? But pi over 2, it's what? It's approximately equal to 3.1415 divided by 2, correct? It's approximately equal to 3.1415 divided by 2. So pi over 2, it's greater than 1, okay? So since pi over 2, it's greater than 1, okay? For all n, equals 1, 2, etc., your 1 over n is greater than pi, or is less than pi over 2, correct? Because 1 over n, that will be less than or equal to 1. If n equals 2, that's 1 half. It's less than 1. But 1 is still less than pi over 2. So you know 1 over n will be less than pi over 2. And this tells us that your sine of 1 over n, okay, sine of 1 over n, this is greater than or equal to 0. Let's say equal to 0. Okay? So, the original series in here. So, let me write this as star or label this as star. Thus, star is an alternating, okay, alternating series. Oops. Alternating series. Okay. And we already showed that the terms sine 1 over n, it's already greater than or equal to 0. The other thing that we need to show here, in order to use the alternating series test, we need to show that this is decreasing, correct? We need to show that this is decreasing. You can explain using your Math 21 knowledge or math, your pre-calculus knowledge, you know that your sine function, it's an increasing function from 0 to pi over 2. Okay? So what does that mean? As you decrease your z from pi over 2 to 0, sine z will also decrease. Okay? But that's equivalent to saying that as you increase your n in here, since n is a denominator, 1 over n is also decreasing. Okay? And therefore, sine of 1 over n will also decrease as n increases. So you can explain it that way. Okay? You can explain it in another way. Use your derivative test. Okay? So consider f of x. Okay? Consider f of x equals sine of 1 over x. Okay? On the interval 0 to pi over 2. Take note, I am not including 0 because 1 over 0 is undefined. So it's not part of the domain. Okay? Sorry, why am I using this? Our x, no, I need my x to run from 1 to plus infinity. I need my x to run from 1 up to plus infinity. And in this case, we can include your 1 here. Okay, you can include your 1 here. So we have the function f of x. Okay, we have the function f of x, which is equal to sine of 1 over x, and we have the interval. This function is continuous, but what we actually need is the derivative, and this is differentiable. So let's get the derivative. F prime of x, this is equal to what? So derivative of sine x, that's cosine of 1 over x. So I mean, derivative of sine of 1 over x, it's cosine 1 over x times by chain rule, derivative of 1 over x, that's negative 1 over x squared. Correct? Correct? But notice, just like in this explanation, your cosine 1 over x, it's greater than or equal to 0 on this interval. Okay? But you have negative of 1 over x squared. Okay? So this is less than 0. Okay? On the interval 1 to plus infinity. Okay? Therefore, f is decreasing. So f is decreasing, particularly, okay, this sequence here, sine of 1 over n, okay, so sine 1 over n is also decreasing, is also decreasing. So now we have positivity and we have monotonicity or the decreasing function here. What's left to do is to find the limit of sine of 1 over n as n approaches infinity. Moreover, so let's do it here. Moreover, limit of sine of 1 over n as n approaches plus infinity. Okay? So what do we get? As n approaches plus infinity, so your n here increases without bound. So you will have 1 over something very, very, very large. And that becomes sine 0. And I mean, that becomes 0 here. So sine 0, okay? But sine 0, it's equal to 0. Okay? And therefore, by AST, by alternating series test, okay, star is convergent. Okay, star is convergent. Now, although the instruction here is to determine whether the series is convergent or divergent, let us give more conclusions. Since this is convergent, let us determine whether this series here is absolutely convergent or conditionally convergent. Okay? So now, let us consider the series. Okay? Series absolute value of negative 1 to the n sine of 1 over n. Okay? And from 1 up to plus infinity. But this guy here, this is just sine of 1 over n. So we sum them up as n runs from 1 up to plus infinity. Okay? And how do we compute the limit of this? We can use limit comparison test. Okay? Okay? Now for this, we compare with the series 1 over n, and from 1 up to plus infinity. Okay, I think this was already shown in one of the lectures, but let us do it here. So we compare this series with this harmonic series, which is divergent. Let us write that, which is divergent. So we use limit comparison test. Okay. Observe that the limit of your sine 1 over n divided by 1 over n as n approaches plus infinity. Okay. You can rewrite this as the limit of sine u over u. Okay. U goes to 0 from the right. As n approaches plus infinity, 1 over n goes to 0 from the right. So if you replace your 1 over n with or by u, you will have sine u over u. And u approaches 0 from the right. And recall that this is just equal to 1. And this is greater than 0. Which means that this guy here is divergent. Okay. So the series sine 1 over n, and from 1 up to plus infinity, this one is divergent by limit comparison test. Okay? So the original series is convergent, but it is not absolutely convergent because this guy here is divergent. Okay? Therefore, let me write it here. Therefore, the series negative 1 to the n sine of 1 over n is conditionally convergent. Okay? Question? So there's a question here. Sir, paano naging 1 yung limit ng sin u over u as you approach a 0? You should have done this from your Math 21. But notice, sin u, as you approach a 0, that's what? Sin 0, which is 0. As you approach a 0, the denominator, this is also 0. So you can use your L'Hopital's rule. And for your L'Hopital's rule, you get the derivative of sin u, that's cosine u. And then denominator derivative is just 1. And what is cosine 0? That's 1. So this should have been taught when you discuss L'Hopital's rule in your Math 21. But in any case, if you have something like this, you can always use your L'Hopital's rule para makuha mo kaagad yung 1. Okay? Well, hindi ko na ginawa yung L'Hopital's rule dito sa part na to kasi this is actually a known limit. Okay, this is a known limit. So basically, dapat you know that by heart. Pero kung hindi mo pa nakikita or kung hindi mo siya maalala, syempre, gamitan mo na lang ng L'Hopital's rule. Applicable naman si L'Hopital's rule. Okay? So, sa first example natin, meron tayong absolutely convergent series here. And then here we have the conditionally convergent series. Let's consider the next example. So determine whether the series is convergent or divergent. If convergent, determine whether it is absolutely or conditionally. Now, if you have a series, okay, with terms involving factorials, okay, if you have a series with terms involving factorials, use ratio test. That's the first test that you will use. So kapag meron ka nakikitang factorial, ratio test agad. Okay? So in here, we have, this is your A sub n. Okay? So we want to get the limit of A sub n plus 1 over A sub n with the absolute values. Okay? And goes to plus infinity. But this will just be what? The limit n approaches plus infinity. Let's see. Absolute value, A sub n plus 1. So you replace your n by n plus 1. So you will have negative 3 raised to 3 times n plus 1 divided by, you have your n plus 1 factorial. And then times. Times na lang, kunin na lang natin yung reciprocal ni A sub n. So this means you will have n factorial divided by negative 3 raised to 3n. Then close natin si absolute value. And then, sulat uli natin, limit as n approaches plus infinity. Ito, expand lang natin. We distribute this 3 over this n plus 1 and then i-separate na natin si negative 3 to the 3n at saka si negative 3 raised to 3. So you will have negative 3 raised to 3n times negative 3 raised to 3. And then sa denominator dito, we will have n plus 1 times n factorial. So definition of factorial. And then in here, let's just write this. You have n factorial over negative 3 raised to 3n. And as you can see, negative 3 raised to 3n will cancel this guy. The n factorial will cancel this guy. So you'll be left you'll be left with the limit as n approaches plus infinity. And then, tanggalin na natin yung negative dito kasi may absolute value naman tayo. So, this is just 3 to the 3 divided by n plus 1. And numerator is constant. Denominator goes to plus infinity. This is just equal to 0. And this is less than 1. Therefore, by ratio test, the series negative 3 raised to 3n divided by n factorial and from 1 up to plus infinity is absolutely convergent. So absolutely convergent. Okay? Question. Okay? Let's look at the next problem. So determine whether the series is convergent or divergent. So you have the sum 2n factorial divided by n to the n. So again, you have some factorials here. Ratio test ka kagad. Okay? So ito, label natin to as a sub n. Okay? So we want to find now the limit, absolute value, an plus 1 over an. And from, or n goes to plus infinity. So ano mangyayari? Yung mga n for the numerator here, or for the terms a sub n plus 1, papalitan natin yung n ng n plus 1. So, magkakaroon tayo ng 2 times n plus 1 quantity factorial divided by n plus 1 raised to n plus 1. Okay? So, absolute value and then times. We have n raised to n divided by 2n quantity factorial. Okay? And then close the absolute value. But take note, these are all positives. Okay? So, pwede natin tanggalin talaga si absolute value. That's 1. Second, distribute natin si 2 dito sa n plus 1. Okay? So, we have the limit. You have 2n plus 2 quantity factorial. And then, ito, sa part na ito, gawin natin, pag-iwa-hiwalayin natin. Okay? Ihiwalay natin yung isang n plus 1. So, you will have something like n plus 1. And then, you multiply this by n plus 1 raised to n. Okay? And then, for this, just write this n to the n. And in here, you have quantity 2n. You get the factorial. So far, so good. Okay. Tignan natin to. Si 2n plus 2 factorial, okay, gamitan natin ang definition of factorial. So by the way, don't forget itong index natin. Your n must go to plus infinity. So anyway, you have now the limit as n goes to plus infinity. Si 2n plus 2, pwede mo siyang isulat as 2n plus 2 times 2n plus 1 times 2n factorial. Okay? So 2n plus 2 times 2n plus 1 times 2n factorial. So, yan na yung 2n plus 2 factorial. So, denominator, you just have n plus 1 times n plus 1 raised to n. And then, here you have n to the n over 2n quantity factorial. So, ano yung mga magka-cancel? Itong 2n factorial, magka-cancel. And then this guy here, 2n plus 2, pwede mo i-factor si 2. So, makakancel si n plus 1 here. Correct? So, this guy here will cancel this, but you will be left with 2. Okay? And then, itong n to the n over n plus 1 to the n, pwede mo na yan pagsamahin. Okay? Pagsamahin mo na lang sa isang exponent, which means that ano mangyayari dito? You will get limit n approaches infinity of 2 times 2n plus 1 times you have n over n plus 1 raised to n. Okay? And then what will happen to this? Itong part na to, particularly this n over n plus 1 raised to n, pwede mo isulat to sa exponential form. And then you get the limit. So you can compute this by adding 1 and subtracting 1 in the numerator. So you can simplify that. But you can always rewrite this in exponential form. Yung e to the a ln of x, if you remember that. So if you have your a to the r, let's just use a to the r. This is e to the r ln of a. So you can always use this. Which means this guy here, you will have the limit as n approaches plus infinity of 2 times 2n plus 1. And then you will have here n or e raised to n ln of n over n plus 1. Okay? And then, of course, this guy here, it will go to plus infinity. But you have to check that this will not go to 0. Kasi kung magpupunta to sa 0, that becomes infinity times 0. It's an indeterminate form. Correct? It's an indeterminate form. So, i-check rin natin yung limit na ito. And you can use your L'Hopital's rule or you can use your the other ways. Particularly itong n times ln of n over n plus 1. Okay? So, paano ba yan? So, let's do that aside here. Side in here. Limit. Sulat natin na x ln of x over x plus 1. X approaches plus infinity. Okay? Take note, as x approaches plus infinity, itong limit na nasa loob, it's just 1. So ln of 1, that's 0. So you will have infinity times 0. It's an indeterminate form. Okay? So what you're going to do, okay, is to rewrite this into, so how? How are we gonna rewrite this? You will have limit as x approaches plus infinity. Let's try this guy here. ln of x over x plus 1 all over 1 over x. So this becomes 0 over 0. And we can use L'Hopital's rule. And then see kung saan mapupunta ito. So this is 0 over 0. Okay? So L'Hopital's rule, this is equal to the limit as x goes to plus infinity. So 1 over this guy here, you will have x plus 1 over x times the derivative of this guy. Low derivative of high minus high derivative of low over low, low. Correct? So you have your x plus 1, that's low. Derivative of high, that's just 1. Minus high, which is x. Derivative of low, what's the derivative of low? It's still 1 over low squared. X plus 1 squared. And then in here you have the derivative of 1 over x, that's negative 1 over x squared. Okay? But let us simplify this. You will have the limit as x approaches plus infinity. In the numerator, this x and x here will cancel. And then here, your x plus 1 here will cancel one of the x plus 1s here. Which means that you will have negative 1 over x squared in the denominator, while in the numerator, you will have 1 over x times x plus 1. And what's the limit? This is equal to, as x approaches plus infinity, try to check. This is just negative 1. Just rewrite this guy here. Okay? Mapupunta ito sa numerator. So you will have x squared over x times x plus 1. Pero polynomial over polynomial lang yun. Tama? So we just take the leading coefficient. Okay? We just take the leading coefficient, which is now negative 1 over positive 1. So you just have negative 1. So try to complete the details for this part. So details. Details, please. Okay? But in a sense, you just have e raised to negative 1. And this guy here, it's going to plus infinity. So the point is, this will just go to plus infinity. So this guy here, this will go to e raised to negative 1. So this is plus infinity. This guy here, it's divergent. That's the whole point. So the series to n quantity factorial divided by n to the n, and from 1 up to plus infinity, this is divergent by the ratio test. Okay? Question? Next example here. So we have sum from n equals 1 up to plus infinity, you have n to the n over e raised to 3n. Now, kung may makita kang factorial dun sa mga terms, you immediately use ratio test. Ngayon, kung lahat ng expression sa terms mo ay nag-i-involve ng raised to n or some combinations of that, immediately use root test. Okay? You immediately use root test. So in here, this is your a sub n. So we want to get the limit absolute value of a sub n raised to 1 over n going to plus infinity. So let us rewrite. Let us put the given an. You have n to the n over e raised to 3n absolute value raised to 1 over n. But this is just what? The limit as n approaches plus infinity of n over e cubed. So we immediately conclude that this is just plus infinity. Denominator, it's constant. Okay? Numerator goes to plus infinity. So this is plus infinity. So the series n to the n over e to the 3n and from 1 up to plus infinity is divergent by root test. Okay? So let me do this as my last example. I still have, after this, meron pa akong mga tatlong examples pa. Pero wala na tayo, dahil na tayo sa oras. So idadagdag ko na lang siya when I upload this recording. Okay? So anyway, so this time you have the series n raised to the n over e raised to 3n squared. So again, we have power or we have exponent n in all the terms, okay? On all the terms of the, or on all the expressions of the term. So definitely, we use root test. So we get the limit, absolute value of a sub n raised to 1 over n as n approaches plus infinity. We now have the limit as n approaches plus infinity n to the n over e raised to 3n squared. And then we raise this to 1 over L. So, may pinagkaiba siya, no? Sa previous example, kanina 3n lang. This time, you have 3n squared. So, what will happen after getting the nth root here? Sa numerator, makakancel itong n na exponent. So, n na base na lang yung matitira. Sa denominator naman, n squared ito eh. So, n squared over n, that's just n. So, may maiiwan kang e to the 3n dito. Okay? And then, let's do the L'Hopital's rule. So, let's do the formal computation here. We replace n by x. Okay? So, limit as x approaches plus infinity of x over e to the 3x. And this is infinity over infinity. So, we can use L'Hopital's rule. And now we have the limit as x approaches plus infinity. In the numerator, we just have 1. While on the denominator, we have 3e to the 3x. And this goes to 0. Or the limit is equal to 0. And this is less than 1. So, by root test the series sum n to the n over e to the 3n squared n from 1 up to plus infinity is absolutely convergent. Okay? So for our next example, we have the following. We have 1 minus 2 factorial over 1 times 3 plus 3 factorial over 1 times 3 times 5 minus 4 factorial over 1 times 3 times 5 times 7 plus until we have negative 1 raised to n minus 1 times n factorial all over 1 times 3 times 5 times blah 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 times 2n minus 1 plus so on. So basically, the first few terms were enumerated, and we have this as our general term. So this means that we actually have the series, okay, negative 1 to the n minus 1. And then you have n factorial over 1 times 3 times 5 times you have 2n minus 1. And then your n starts with n equals 1. And then this is up to plus infinity. Okay? So, we have seen a similar example in the lecture. This time, we get the reciprocal of this term here. Okay? So, in the numerator, you have the n factorial. In the denominator, you multiply the first odd integers, first few odd integers. Okay? So, we want to determine whether this is convergent or divergent. Okay, and if it is convergent, we determine whether it's absolutely convergent or conditionally convergent. So, well, first, this is an alternating series. Okay, this is an alternating series, and then let's see if we can use the alternating series test. Okay, so here, let us consider our Bn to be that n factorial over 1 times 3 times 5 until times 2n minus 1. And definitely this is greater than or equal to 0, okay, for all n. For n equals 1, 2, etc. So notice here you have the first term to be 1, the second term to factorial over 1 times 3, etc. So the terms are positive. Okay. Next, we want to know if this is decreasing. Okay. We want to know if this is decreasing. And again, let us use the following criterion. You have Bn plus 1 divided by Bn. So we want to show that this is less than or equal to 1. Okay. So this is what we want to show. Because if this is true, then Bn plus 1 is less than or equal to Bn, and therefore this is ultimately decreasing. And the reason why we are going to use this is because we can use ratio test from this after getting the term Bn plus 1 over Bn. Okay? So let's see. Bn plus 1 divided by Bn. So in here, we have what? N plus 1 factorial divided by 1 times 3, okay, times 5. So 1 times 3 times 5 times you have 2n minus 1 times 2 times n plus 1 minus 1. Okay, so that's our Bn plus 1, sorry, Bn plus 1. And then for the Bn, Since it's in the denominator, let's just get the reciprocal of this. So you will have 1 times 3 times 5 times you have 2n minus 1 divided by n factorial. So note that on the denominator, you are just multiplying the first few odd integers, which means that 2n plus 1, the next term to that is the next odd integer. And you will see that if you multiply this 2 into this n plus 1, this guy here will be simplified into 2n plus 1. So that should make sense. Okay? And this guy here, you can rewrite this as n plus 1 times n factorial, which means we can cancel the n factorial. And then this 1 times 3 times 5 until times 2n minus 1 will cancel the same here in the denominator, so that we will be left with n plus 1 divided by 2n plus 1. Okay? And clearly, this guy here, this is less than n plus 1 divided by 2n plus 1. You added a positive integer in the numerator, so this becomes bigger compared to the numerator of this. But this guy here, it's 2n plus 1. So this guy will cancel the 2n plus 1 denominator, meaning this guy here is actually less than 1. So we have shown that Bn is decreasing. So Bn, this one is decreasing. So AST applies. Oops. Yeah, AST applies. AST applies. Okay. And last thing to check is the limit. Okay, is the limit of Bn equals 0. Okay. We have here now limit of Bn as n approaches plus infinity. But what is this? Okay. What is this? We have actually instead of applying AST here, we now know that Bn plus 1 over Bn is somewhat less than 1. So what we're going to do is apply the absolute convergence test immediately. Okay, we apply the absolute convergence test immediately. So let us remove this part. Okay, there's no need to apply this. We directly use absolute convergence test. Okay, so how do we do that? So now, so give me more space here. Now, we consider the absolute values of the terms. So negative 1 to the n minus 1 n factorial over 1 times 3 times 5 times 2n minus 1. Okay. And from 1 up to plus infinity. And this is just this guy. This guy without the negative 1 raised to n minus 1. So this is just the sum n factorial over 1 times 3 times 5 times you have 2n minus 1. And from 1 up to infinity. So if we show that this is convergent, then this guy here is absolutely convergent because we use the absolute convergence test. Now, to show that this is convergent, we use ratio test. Okay? Now, next, we want to find the limit absolute value of your Bn. I labeled that Bn, so I'm going to use Bn. So Bn plus 1 over Bn as n approaches infinity. But we already have simplified it to this expression. So you have the limit as n goes to plus infinity of n plus 1 divided by 2n plus 1. And since you just have a polynomial over polynomial, both of degree 1, we just need to get the leading coefficients. And this is equal to 1/2, which is less than 1. Okay, which is less than 1. And therefore, by ratio test, the series negative 1 to the n minus 1 n factorial over 1 times 3 times 5 times 2n minus 1 and from 1 up to plus infinity is absolutely convergent. Is absolutely convergent. Okay? So actually, we can just remove this part because we are not going to use the alternating series test. But anyway, this is an alternating series, so you might, at first glance, you will think of using alternating series tests. It's totally fine, okay? It's totally fine. But if you started with this solution, then you will still get the full points, okay? Question. Now, let us consider this. Determine whether the series sum an is absolutely convergent, conditionally convergent, or divergent if the terms an satisfy the following. A sub 1 equals 2 and a n plus 1, this is equal to 4n plus 3 over 5n plus 1 a sub n. Okay? For n greater than or equal to 1. So all we need to do, we just need to use ratio test. So solution. So now, so one has a sub n plus 1 divided by a sub n. We get the absolute value of this and we get the limit of this as n approaches infinity. But if we plug in a sub n plus 1 over a sub n, okay, look at this. We just divide by a sub n here and you will just get that 4n plus 3 over 5n plus 1. Okay? And as n approaches infinity, this is just 4 over 5. And again, this is less than 1. So, the series a sub n with this information is absolutely convergent. Okay? So you don't even have to know the form a sub n. Okay? This information here, a sub 1 equals 2 and a sub n plus 1 equals this guy here is enough to determine whether this is absolutely convergent. Okay? Okay, so for my last example, so for which values of x does the series converge? So this is a preview of of our next lecture. Okay, so we have this series. We have a variable x, and we want to know for which values of x that this series will converge. So we'll just use ratio test. Okay, we'll just use ratio test. So solution for um, for all n equals 0, 1, 2, etc. We let a sub n be equal to that x to the n over n factorial. Okay, then we will try to find the limit as n approaches plus infinity of the absolute value of a sub n plus 1 over a sub n. And in here, we'll just have the limit as n approaches plus infinity. For our a sub n, you have your x to the n plus 1 divided by n plus 1 factorial times. For our a sub n, sorry, for a n sub 1, we have this. And then for our a sub n, it's on the denominator. So let's copy this, but we have to take the reciprocal. So n factorial over x to the n. Of course, just like before, this guy here, you can write this as x to the n times x, while this guy here, you can write this as n plus 1 times n factorial. So you can cancel the x to the n with this x to the n here, and then the n factorial here and here, which means that we have the limit n approaches plus infinity. So we'll be left with what? Absolute value of x to the n over n plus 1. Sorry, x only in the numerator and then n plus 1 on the denominator. Take note that x is a variable, so it can have positive or negative. So we should retain the absolute value in the variable x. So you have limit as n approaches infinity, absolute value of x over, then you have n plus 1. So you can remove the absolute value in the n plus 1 because n starts from 0 and you have n plus 1. This is always positive. Furthermore, your x, it's free of this n. So you can actually take this out. Okay, you can actually take the absolute value of x out. Okay, so this guy here will be equal to the absolute value of x limit n approaches plus infinity of 1 over n plus 1. Okay? By the way, so you are taking the limit of a sub n plus 1 over a sub n. Particularly, you have a denominator a sub n, which means that you will get denominator x to the n. So at the beginning, you have to write that condition. So then for x not equal to 0, so this is important so that we don't have a denominator 0 here. Okay? But anyway, absolute value of x limit 1 over n plus 1 as n approaches infinity. This guy here will be 0 as n approaches infinity. So if you multiply any x or absolute value of x, this will always be 0. And this is less than 1. Okay? This is less than 1. Now, This means that this series, okay, is absolutely convergent, okay, for all x not equal to 0, at least for this part of the solution. So by ratio test, the series x to the n over n factorial n from 0 to plus infinity is absolutely convergent for x not equal to 0. Okay? Just for this part of the solution, we have this conclusion. Okay? And definitely, when x equals 0, this is just the sum of 0. Okay? Moreover, for x equals 0, okay, we just have the sum of 0. Okay? The sum of 0 to the n over n factorial, n from 0 to plus infinity. Okay? And from 0 to plus infinity. But this is just what? This is just equal to 1. In here, we are assuming that when n equals 0, you just have the 1 over 0 factorial. Of course, you don't have 0 to the 0. That's undefined. Okay? So this guy here, this is expanded as 1 plus the sum of 0 to the n over n factorial, n equals 1 to plus infinity. And this guy here, this is just 0. So this is equal to 1. So it's still convergent. Therefore, we have, the series x to the n over n factorial, n from 0 to plus infinity, is convergent for any x, for any real number x. And that's it. That's the solution for this problem. Again, okay? So again, possibly this guy here, it's not as clear, but you will learn later that if you have something like this, the the the, the term with n equals 0, it's just your constant term. Okay? It's just your constant term. And the x to the n is just equal to 1 when n equals 0. Okay? When n equals 0. So that's my last example. So thank you, and I hope you learned some techniques. And yeah, goodbye.